Okay, so now we are going to discuss about the logic derivations of set theory. So now we will talk about the basic definitions of set theory. The first basic definition being a subset. Now, subset is like, if you just intuitively see, it's like if there is a set A and it has the elements 1 and 2, and if you have a set B and it contains, say, the elements 1, 2 and 3, then you say that A is a subset of B, because A contains the elements which B already has. So now, to formally define a subset, we can write it as, if every element of set A is also an element in set B, then A is a subset of B. So now if we write this logically, so first we have to analyze what the statement says. First of all, obviously there is a pair of if and then, like if and then pair is there. So this somewhere implies that there might be a single implication. We will get on to this. Then the next hint which we get is there is every, and another hint which we get is also. So now these three keywords, something is revolving around these three keywords. So let's see. First of all, because of every, we are able to say that there is a quantifier coming, and obviously that quantifier is for all quantifier. I'll be representing that for all quantifier with a V. So over here this statement reads as every element of set A. So I'll be representing an element of set A with the notation of set A as XA, and similarly an element of set B, I will be representing it as XB. So now over here it says every element of set A. So that means that for all X, every element of the set A, that means that before actually writing it in logic, there is a crucial part in this sentence, that is element in set A also in set B. Over here, this part, what this part implies is that if an element is in set A, then it is also in set B. So over here also just means this. But now interestingly enough, it's not a double implication, it's a single implication. So if the sentence was something like element in set B also in set A, this implies a different thing and this implies a different thing. Over here the first sentence implies that an element in A, that is if an element is in the set A, then it should be in B also. But over here this sentence implies that if an element is in set B, then it should be in set A. So it's not a double implication, it's a single implication. So writing this in logic is really easy. It can just be written as, if an element is in set A, then it is in set B. Now combining this with the quantifier every, we arrive at, for all the X present in the domain given by the question or by the assumptions, that is mostly we take real numbers only as our initial domain, but that changes. So for all the x's, if an x belongs to a set A, then it should also belong to the set B. Now this is just one part of the definition. We have covered also over here means a single implication. The only thing which is left is an if then. Now this is we can say that it's a false kind of thing in English, because in English we usually exchange if and only if with if then. Over here, if we just read it in English, then it makes sense, but in a logical way it doesn't make sense, because it's saying that if every element of set A is also an element in set B, then only that A belongs to B. A is a subset of B. But if we read it opposite, like for example, if A is a subset of B, then every element of set A is also in set B, which makes sense over here. So this over here, in this case, if then is not an if then, it's an if and only if. So what this basically becomes is, if this happens, then a double implication A belonging to B. So now if we read this, A is a subset of B if and only if for all the x, if x belongs to a set A, then it belongs to a set B. Now we have written it in logic, but we also need to test the logic. So obviously, let's first of all just verify this. So let our first example be that let A equal to just one element A1, and let B be a set like 1 and 2. So over here there is a quantifier for all, and if we take our domain as the biggest set in the question, so over here the biggest set in our question is B, so our domain is B. Our domain over here means that we will be checking over all the elements of B. It doesn't need to be always B, it can also be like you are checking over all the real numbers, but over here it makes sense. I'll get onto that in a moment, but for first let's check for B. That is, if x is 1, that means that first we need to see that does 1 belong to A or not. It does, so it's true. Now we need to see if 1 belongs to B or not. It does, so this is also true. So this means that true implies true. Double implication A is a subset of B. So this just implies that A is a subset of B, and it's a true statement. Now as this is a for all, we need to check the other values also, that is x equal to 2. Does 2 belong to A, which is false? Does 2 belong to the set B? Yes, it does, so it's true. So now does false imply true? Yes, it does, so this as a whole is again true. So we have checked over all our domain, and for all the values it's coming true. So hence we can conclude that A is actually a subset of B. Now expanding upon what I said about the domain, now for example, if B was something like 2, 3, and if we took the domain as B, then this would be wrong. What a smart move would be to do is take the domain as the union of all the sets which are given. So that means A union B. If this was our domain and then we did our checking, then this would be a more practical and logical way to approach it. So if we do this now, so now our domain becomes 1, 2 and 3. So we need to check over 3 values. So for x equal to 1, does 1 belong to A? Yes, it does. Does 1 belong to B? No, it doesn't. So this is false. So now over here, this comes as true implies false. And because true implies false is false, so A is not a subset of B. And so we needn't check these conditions which are given below. So now we can obviously think of a condition where the first half of the logic statement which we gave will always be true. That is, the first half is this. Now to make this always true, if we arrive at a conclusion that false implies true always or false implies false also, if the first half, that is XA, is always false, then this whole condition will be true. So now it is possible in one case, that is if we take an example where A is an empty set and B, let it be anything, let it be the whole real numbers. So now our domain over here is, interestingly, A union B. So that just implies that it's the whole of real numbers. So we don't know from where the real numbers start. So we need to prove this by induction only, but we need to run some tests. So our first logical test would be that let's see if a number such as 0, let's see that if 0 satisfies this condition or not. So does 0 belong to A? Obviously it doesn't. Does 0 belong to B? Obviously it does. So our logical statement would be false implies true, double implication A subset of B. So this just implies this whole will be true. False implies true. So true double implication A subset of B. So hence A is a subset of B. So now there are uncountably infinite numbers in a real number set. So we need to prove this by induction only, that all of the elements in B are not in A. So always this condition will come that false implies true. So A will always be a subset of B. And so we can arrive at a conclusion that an empty set is always a subset of any set. So U is a universal set which can be anything. Now interestingly enough, that our first part of the logic statement, which was that it's XA now first half, that is the single implication part, this has 4 more parts, that is its inverse, converse and contrapositive. Let's see its contrapositive then. Its contrapositive would be that an element is not in the set B and the element is also not in the set A. So now if we analyze upon this statement, then it should be equivalent to the statement above. So let's just take a short example, that A let A be 1 2 and let B be 1 2 3. So again our domain over here is B, that is 1 2 3. So let's go with x equal to 1. Does 1 belong to the set A? Yes, it does. Does 1 belong to set B? Yes, it does. Now, is like if we not it, then we get false. And if our first condition in the single implication is false, then we needn't check it further because it will obviously be true. So now let's do the same for x equal to 2. Does 2 belong to the set B? Yes, it does. This needs to be true. Wait. And so if we not it, this gives me false. So again we needn't check it again. Now for x equal to 3, does 3 belong to B? Yes, it does. And if we not it, it gives us a false. So hence we can conclude that A is a subset of B.